Okay, welcome everyone. This is our first video for Math 0931, Intermediate Algebra Part 2. Because this class is Part 2, we are sort of picking up where the Part 1 class, Math 0930, left off. So the way I structured my Part 1 class is I just numbered the lessons from 1 through 18. If you took that class with another instructor, they might have gone by another numbering system or the chapter sections in the textbook, etc. So I'm picking up where I left off. The topics that you would have covered with another instructor would have been the same. They might have been numbered differently, but in my 0930 class, we covered lessons 1 through 18. So we are starting with lesson 19 on exponents. So that's what this video will cover. So I'll be going through this PowerPoint and I'll be using some technology to write on the screen so you can kind of follow along that way. The PowerPoint that I'm using is also available in Blackboard if you'd like to print a copy for yourself, but you should be fine just following along with the video and taking notes in whatever way works for you. All right, so let's start this slideshow here. All right, so we are going to be learning about exponents. So you should already know what an exponent is. You would have seen exponents when we learned about order of operations. What we are learning about here is rules for how we can simplify algebraic expressions that involve exponents. There's going to be variables here. We're not solving for a variable. These are not equations. These are expressions that we will be simplifying. So we're going to learn some rules for how we can simplify more easily with exponents. So let's take a look at our first one here. This is called the product rule for exponents. So here's the rule we're going to use. X to the m times x to the n is equal to x to the m plus n. This rule is telling us when we have a product or multiplication, as long as our base number is the same, then what we can do is add the exponents. Let's see some examples of this. Okay, so we have two examples here of products. Remember, the word product just means multiply. All right, so with my first example, I'm going to simplify it without actually using the product rule, just so we can make sense of why we can use a shorter way. So let's do this the longer way. X to the fourth, what that really means is we are multiplying x times itself 4 times. And then x to the third, we're multiplying x 3 more times. So all you need to do here is recognize how many x's are being multiplied. There's 4, and then there's 3 more. So what we can do is add those exponents. We get x to the 4 plus 3, which is just x to the 7th. This is our answer. This is our simplified answer. So x to the 4th times x to the 3rd can be written as x to the 7th. That's it. Okay, that is our answer. So we are simplifying an expression. Oftentimes we're starting off with more than one variable written here, and we should end up with just one single expression at the end. So you can see how I wrote this out. You can always do that if you get the rules mixed up as we learn more and more of them. You can always write it out to kind of remind yourself what operation you're going to be doing with the exponents. So let's try another one with the k example over here. First thing I need you to know is when you have a variable that does not have an exponent, it actually does have an exponent. So there's always a 1, even if you don't see it written there, and you usually won't. There's always a 1 exponent. So that's good to know because we're going to need to add that 1 with these other exponents. Now, I'm not going to write this one out like I did in the previous problem because it would be a lot of k's written out. I'd write 1k here, then 10 more, then 14 more after that, and I might lose count. So what we can do is use our product rule, and we can add the exponents. Now, we can actually add all of them. I'll break it down and do it in a couple steps. So 1 plus 10 would be 11 for the first two. And then we'll add 11 plus 14, which is 25. Okay, that's a little bit more detailed than what you might show in terms of showing your work. If you want to just add all those numbers together right away, that's great. So 1 plus 10 is 11, plus 14 is 25. So k to the 25, or k to the 25th power, would be how we would simplify this expression. So we're keeping the same base number, or variable in this case, and we're just adding the exponents. So that's our first rule. This is the product rule. Okay, there's going to be a few more rules coming up. So let's keep going. Okay, the next rule is called the quotient rule. Okay, quotient is a word that we use to refer to division problems. So you can see with division, we don't often see a division symbol, we see it as a fraction. So when you see a fraction problem, recognize it as division. So this rule is kind of the opposite. When we multiplied, we added the exponents, but now when we divide, what we're doing is subtracting the exponents. So just like last time, I am going to do one problem kind of the longer way, and then we'll recognize why the rule works, and then we'll take it from there and actually use the quotient rule. Okay, so let's simplify this one. Y to the 8th divided by y to the 3rd. Now I know we have a rule for this, but let's see if we can understand where the rule comes from. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So I've written out y to the 8th 8 times. Okay, and now I'll do the same thing for y to the 3rd. Y times y times y. Okay, so as you hopefully remember, when we reduce fractions, we look for common factors that we can cancel out. So that's really what we have here. We have a common factor of y, then we have another common factor of y, then we have another common factor of y. Each time that happens, we can essentially cancel these out because anything divided by itself is equal to 1. So y divided by y is just 1. Okay, so that's why I can cancel out these common factors. Now notice that I canceled out 3 pairs of factors of y. Look how many are left. There's 5 factors left, so that's y to the 5th. This is our final answer. Now let's go back and actually find the answer using the quotient rule, which is meant to be sort of a shortcut. Okay, so sort of the official way, the official way to do this would be like this: y to the 8 over y to the 3rd. We can just write y to the 8 minus 3, which will give us y to the 5th. Okay, so notice that you subtract the top exponent minus the bottom exponent. Now sometimes the top exponent will be smaller and we'll end up with a negative exponent. We'll get to that later. There's something else you need to know about that, which we'll get to one thing at a time. So this was the quotient rule. When you see a fraction, that's a division problem. As long as the bases are the same, what you do is subtract the exponents, the top exponent minus the bottom exponent. Okay, let's do a second example. This time, instead of y or x or any other variable, we actually have a number 2 as our base. Okay. I want to tell you that this is still the same idea, but sometimes what students do is they see the number like 2 and they want to cancel out the 2's right away. I didn't really do that without actually writing out the full problem, so be careful. If I were to write this one out, 1, 2, 3, 4, 5, 6, 7, 8, 9, I could barely fit it in there, so that's 9 factors of 2. And then 2 to the 5th, 1, 2, 3, 4, 5. There's a reason why we have these rules, right? We don't want to write it out every time. Okay, but essentially what we can do here is cross out 1, 2, 3, 4, 5 factors of 2, and we're left with these 4 in the numerator. So that's essentially 2 to the 4th. So an easier way to do that would be to just do 2 to the 9 minus 5, which is 2 to the 4th. Now because this is a number, we can simplify it more and figure out what that is. 2 times 2 times 2 times 2. 2 times 2 is 4. Let me start again, sorry. 2 times 2 is 4, times another 2 is 8, times another 2 is 16. Okay, so 16 would be our true final answer for this problem. You can write it out just to work it out and be sure of your process. But there's a rule here. There's a little formula we can use. So feel free to just do that and subtract the top exponent minus the bottom exponent. 9 minus 5 is 4. Now, if this was x to the fourth, we'd be done. But because it's a number, 2 to the fourth, we were able to simplify even more. Okay, so that was our second rule. We've seen the product rule, and then now we've seen the quotient rule. We're going to keep going. So in my experience, each rule makes sense on its own, but as we add more and more to the list, it can become a little tricky and you might feel like you're losing track of them or getting them mixed up. So just be careful and take your time as you're doing this one. All right, so the zero exponent rule. This one is a little bit strange because it doesn't really seem to make much sense when you first see it. Let's take a look. Okay, so here's the rule. Apparently, anything to the power of 0 is equal to 1. So x to the 0 is always equal to the 1. As long as, this rule works as long as the base is not 0. So 0 to the 0, we don't see that in this class. In fact, you might not even see it until calculus or something like that. So don't worry about that. That's a whole other concept. There's another word for that that we're not going to see in this class. So that's what this is saying, as long as the base is not 0. Okay, so once you see it, just let that go. Assume that the base is not 0, and then we'll simplify. Okay, so these are fairly short problems. According to the rule, anything to the 0 is 1, so y to the 0 is 1. That's it. Not really much to say about it, other than apparently I'm just using this rule here. Now, I do want to take a moment to try to show you why this works. So maybe just a little side note here. I like to show this by kind of showing a pattern. So I'm going to start with 2 to the fourth, 2 to the third, 2 squared, 2 to the power of 1, and then 2 to the power of 0. I want you to see if there's a pattern here. And this is not necessarily a proof of why this works, but hopefully you can maybe see why it needs to be 1 down here for a power of 0. But let's work our way there. 2 to the fourth, we saw in a previous problem, that was 16, remember? 2 to the third, 2 times 2 times 2, that's 8. 2 to the power of 2, that's 2 squared. 2 times 2 would be 4. Okay, so I'll write this one out too. All right, 2 to the power of 1. Okay, anything to the power of 1 is just itself. All right, now maybe you're noticing a pattern for how many 2's there are. What I'd want you to focus on is these answers here. What's happening between each one? 16, 8, 4, 2. They're being cut in half. They're being divided by 2. So if I were to continue that pattern, 2 divided by 2, it would be 1. Now, if most students, if they would guess what the answer is here, they would guess 0. That's the most common guess, and it's understandable. But now you know it's not. 2 to the 0 is not 0. 2 to the 0 is 1. And you can illustrate this pattern with any base. You can do a base of 3, 3 to the fourth, 3 to the third, etc. And then once you work your way down, you'll eventually get to 3 to the 0 is 1. 4 to the 0 is 1. Anything to the 0 is 1. So that's kind of a strange rule. So if you've never heard that before, definitely, add that to your list of things to memorize here. Okay. All right. So that was my attempt at kind of showing you why the answer is 1. If that helped, great. If not, let it go and just say, okay, I'm going to go with the rule that was given to me. All right. Let's do a couple more examples. K to the 10th divided by k to the 10th. Okay, what does this have to do with 0? Well, if I use the quotient rule, 10 minus 10 is 0. And that's why the answer here is 1. Now, look at how that makes sense, right? K to the 10th divided by itself, you can kind of see that it was going to turn into 1 anyway, right? So that's another sort of reason why this ends up working out. Okay, now before you think, oh good, the third answer is 1, it's actually not 1. Why not? All right, there's a 6 here. x to the 0 is 1, but the 6 comes down. So this isn't really 1 for a final answer, it's 6 times 1. So actually the final answer here is 6. Now, if you ended up, if the problem started out differently and the 6 was in parentheses, that would lead to a different answer. And I think we might see that coming up here in a moment. Let's see. Okay, I think we're going to see it later, but I feel like I should make a note of this right now while I'm thinking of it. So I'm just going to make a little space here. Okay, so just slightly different example. Let's say I had, instead of 6x to the 0, let's say it was 6x in parentheses, and that whole expression was raised to the power of 0. So how would that be different? Let's find out. Okay, so we'll add kind of an example D down here. If that was raised to the power of 0, then this whole thing does become 1. So parentheses are super important here. There were no parentheses around the 6, so it kind of had its own exponent on it, 6 to the 1, it's just 6. The only thing that had the 0 exponent was the x, so that became 1. The 6 was still there. 6 times 1 is 6. Okay. Some tricky things to think about there. All right, I'm going to keep going. So I think we're moving on to our fourth rule now. So we had the product rule, quotient rule, 0 exponent rule, and now we're looking at the power rule. All right. So speaking of parentheses, these problems will have parentheses. When we see an exponent outside of parentheses, generally what we're going to do is multiply them. So you'll see me start to draw some arrows here. It kind of feels like we're using the distributive property. That's not exactly what it is, but it sort of feels like it. So you might hear me use the word distribute, even though it's not quite the same thing, but it kind of feels like it is. Okay, here we go. So x to the 5th to the 3rd. Once again, I'm going to write this out, just like we did with some earlier problems, because now this is around the time when people start mixing up the rules and you look at this and say, wait, do I add 5 plus 3 is 8 or do I do something else? Okay, it's going to be something else. So x to the 5th to the 3rd, we could write it like this: x to the 5th times x to the 5th times x to the 5th 3 times. You could write it out even more than that. It gets a little tedious, but write the letter x 5 times, then 5 times again, then 5 times one more time. So there's 3 sets of 5 x's. It's 5 times 3. How many x's are there? There's 15. This is x to the 15th. Okay, so a shorter way to do this is just use the rule and multiply those exponents. Okay, so this is different. So different example. If you were to do x to the 5th times x to the 3rd, that's when you would add them and get x to the 8th. So notice the difference there, okay? This was x to the 5th to the 3rd, okay? So the way I remember this is when I see parentheses, that's when I know I'm going to be multiplying the exponents. Okay, let's do another one. Example B over here. Now, once again, I could write this out 4 times, but there's a rule. Let's just use the shortcut here. Now there's more than one variable. Also, there's a number here. So now I am going to do that thing where I'm distributing my exponent. I am going to be multiplying this 4 by each exponent that we see. Now, what exponent is on this 3? There's a 1 there. 1. Okay, so be careful. We're not going to do 4 times 3 is 12. That's not happening here. This is 3, and then 1 times 4 is 4, like that. So we'll have to simplify that. We'll get to that in a later step before we write our final answer. Now let's work on the x to the 3rd to the 4th. We're going to do, now we are going to multiply 3 times 4 and get x to the 12th. And then we'll also multiply the exponents on the y's. 2 times 4, and that would be y to the 8th. This is not fully simplified because I do have this number, 3 to the 4th. We can simplify that more. 3 times 3 times 3 times 3. It's 9 times 3 times 3. 27 times 3. This is 81. So 81, x to the 12th, y to the 8th would be my final answer here. So that's a harder example using the power rule. So when you have a power of a power, when you have an exponent raised to another exponent, that's when we are multiplying, which is different from the product rule that we learned at the beginning where you're adding. So when you see parentheses, get ready to multiply those exponents. Okay, good. So we're going to build on that right now. We just learned the power rule. This is now something called the expanded power rule. So remember how we just distributed? We distributed that exponent through the parentheses. We're essentially going to do the same thing here. It's just that now we're going to see some fractions. Okay, good. So this rule is essentially saying this. Let me see. Okay, this is what the rule is essentially saying. Take the exponent on the outside of the parentheses and just distribute it to every single term, every single number and variable inside the parentheses. So a to the m, x to the m, b to the m, y to the m. There's these little notes here about certain variables can't equal 0. That's because they're in the denominator. So we just don't want the denominator to equal 0. That would lead to something that's undefined. That's all that little note is saying. Okay, now before I just start distributing everything, recognize that you have a fraction that actually can be reduced. So let's take care of that first, and trust me, that's going to make our work a lot easier because otherwise we'd have to do 12 to the 3rd, 16 to the 3rd. Those numbers are going to get very large, and then reducing will be even harder. So let's reduce first if possible. Okay, so we're just focusing on what's happening in here. We'll deal with the 3 at a later step. So let's just simplify what's happening inside the fraction. We'll take it one thing at a time. Let's start with the numbers, -12, -16. So we can kind of treat that as its own little fraction to work on. Then we'll work on the x's, then we'll work on the y's. Okay, negative divided by negative, that will become positive. So that means I don't need to write any negatives at all in my answer. Now we'll just work on 12 and 16. They do have a common factor of 4. 12 divided by 4 is 3. 16 divided by 4 is 4. So 12/16 reduces to 3/4. Okay. Now let's work on, we'll do the x's next. All right, this is a little tricky. It kind of snuck in here before we were ready. If we subtract these exponents, we're going to get a negative, and we're going to see this very soon, but we're not quite ready right now. So instead, whoops, see, we're about to see it next. Instead, what we can do is we can subtract 7 minus 2, but you just have to keep it in the denominator. Okay, there's going to end up being an x to the 5th in the denominator. And I guess an easier way to explain why that is, it's because the bigger exponent is in the denominator. This is probably a good time to maybe write this out so we understand why that's happening. So let me make some space here. Okay, so I can basically just write out 2 factors of x in the numerator and then 5 factors of x, or excuse me, 7 factors of x in the denominator like this. 1, 2, 3, 4, 5, 6, 7. So what can we cancel out? Well, we can cancel out these 2. X divided by x is 1. And then we can cancel out 2 more. That's 1. And then look, there's 5 factors of x in the denominator. It feels like, sorry, it feels like there's nothing left in the numerator, but it's not nothing, it's 1. Okay, so we end up having a 1 over x to the 5th. So that's a preview of what we're actually going to see next about negative exponents. You kind of just got a little mini lesson on negative exponents, which basically you end up with something in the denominator. Now, I do not need to write a 1 up here because I already have a 3, but just to be super extra thorough, I'll write a 1 and then we'll simplify a little bit later. Okay, so that was a little trickier than we maybe expected. Let's work on the y's now. Y to the 8th over y to the 5th. This is more what we're used to, the bigger exponent on top. 8 minus 5 will be 3. Okay, and that is technically over 1, right? So we do get to put that in the numerator this time. So again, just pay attention when you're subtracting exponents like this. Wherever the bigger exponent is, that's where your variable will end up. Okay, that was a lot of work, but we're not done. We still have this 3 to deal with. Okay, so once again, I'm gonna clear some space. Okay, and what we can start to do is distribute that 3. And now we can finally use that expanded power rule. So we're going to be multiplying exponents as we do that. Okay, here we go. So let's see, I'll just put these together. 3 times 1 is just 3. Okay, so now when I distribute this exponent, be careful, you might think, oh, 3 times 3, 9, but no, it's 3 to the 3rd. Okay, this 3 stays here as a base, and then this exponent kind of gets applied to it. Okay, so we'll simplify that later. Here is where I multiply. So that's tricky, right? So your mind might want to just multiply everything, but you really need to be careful about, okay, where do I just put an exponent and then where do I actually multiply? Here's where we multiply. Because this 3 on the y, that is an exponent. We do get to multiply that by 3. That turns into 9. So notice the difference there. The main difference is the first part, the base was a number. The second part, the base was just a variable. Okay, keep going. Now I'm going to do 4 to the 3rd. And finally, I use my power rule one more time. 3 times 5 is 15. So my last step in simplifying this, I just need to simplify the numbers. 3 to the 3rd, 3 times 3 times 3, that's going to be 27. And then 4 to the 3rd, 4 times 4 times 4. 4 times 4 is 16, times 4 is 64. Okay, so 27 over 64, and then y to the 9th, x to the 15th. And we're done. Okay, so that was a lot. That was the expanded power rule. So there's a lot going on in that problem. And I'll just take a moment now to say, this is kind of what it looks like to show your work. I'm not saying your work needs to match mine exactly, but I would not expect you to go from this original problem to this final answer with nothing in between. You should be showing some kind of process of simplifying. If you're doing an assignment where you're showing me your work, or of course on a test as well. Okay, good. So we're more than halfway done with this lesson. What we have left to look at is some negative exponents, and then we'll kind of put it all together. Okay, so we're getting there. All right, negative exponents. So the main idea with negative exponents is you end up with a fraction most of the time. So I'm just going to write a little note here for us. Here's our formula. X to the negative m is equal to 1 over x to the positive m. A couple things. That 1, some people think you're just flipping the whole thing. Not exactly what's happening. That's where that 1 comes from. That 1 is called a coefficient of the x. So if it was a 5 in front of the x, it would be a 5 here. So 5 x to the negative m would be 5 over x to the m. Just a little note there about where that 1 is coming from. So let's focus on what's happening with the exponent. It started negative, it ends positive. And the x essentially, I think of this as being flipped. Okay, so really 2 things are happening. Something is getting flipped. And then we're making the exponent positive. That's the main idea. Each problem will have its own variation on that, but that is the main idea. Okay, so let's give some of these a try. Number 1, a to the negative 8. Okay, so something's going to flip. It's going to be the a. And now let's make that negative exponent positive. Now what's missing? Oh yeah, a 1. If you end up with nothing in the numerator, put a 1 there. There's a 1 there. Okay, that's it. So see how that one pretty much matches my formula. There's not really much additional work to do there. We're flipping something and then we're making the exponent positive. So in general, we want our final answers to have positive exponents. Let's do something similar here. Okay, so we have this negative exponent, so let's flip something. That's the 5. We'll put it in the denominator. The negative 3 becomes a positive 3. And once again, here's a 1. Now this one does have a little extra work because we have a number rather than just a variable like a. We can simplify 5 to the 3rd. 5 times 5 times 5 will be 125. That's our final answer, 1 over 125. Now you could write this as a decimal. I'll just make a note right now to say we're not interested in decimals for these problems. Everything should be left as a fraction. Okay, let's keep going. Number 3. Something's going to flip. Okay, but see how we're starting out in the denominator? So actually, that x to the negative 2, the flipping means we put it back up in the numerator where the 1 is. Okay, and when I put it up there, I'm also making the exponent positive. Now, what's going on down in the denominator? Well, I guess that, if there's nothing there, there's a 1. So my final answer here is actually just x squared. So that's strange because instead of ending up with a fraction answer like the previous two, we're starting with a fraction, but then when we flip our expression, we move it from the denominator to the numerator. It's not even a fraction anymore. Okay, so that one's a little bit different. Okay, number 4. All right, there's a couple ways to do this. This is a quotient. You could start by using the quotient rule, but I'm not going to do that. It would involve a lot of subtraction with negatives, which people tend to make mistakes doing that sometimes. So instead, let's sort of follow our little process here of let's flip anything that has a negative exponent, and then we'll make the exponents positive. So there's 2 different expressions that have negative exponents. 4 to the negative 5, let's flip that to the denominator, make it 4 to the 5th. And then, can you see where this is going? 4 to the negative 3, that was in the denominator. We're going to flip it back up to the numerator. Now it's 4 to the positive 3. Okay, so there's still more to do. We still do need to subtract these exponents, but I think it will be easier now because we're just dealing with positive numbers. 3 minus 5 is negative 2. And now it's almost like I'm back at the beginning of one of these earlier problems. 4 to the negative 2, we would write 1 over 4 squared, which is 1 over 16. Okay. Lots of little steps in that one, and there's more than one way to work that one out. So let's see. Could I have gone a different way here? I mean, if we had subtracted earlier, negative 5 minus negative 3, like that, we would have gotten 4 to the negative 2 and then ended up with the same result at the end. I would be worried about mistakes happening with that, though. The most common one being, oh, negative 5 minus 3, that's negative 8. Well, no, it's negative 5 minus negative 3. That's an easy thing to miss. Another thing we could have done, which I had mentioned earlier, is back at this step with the 4 to the 3rd over 4 to the 5th, we could have actually just subtracted 5 minus 3, but just kept the answer in the denominator. So 5 minus 3 is 2, but just put the 2 in the denominator. So that 4 squared stays in the denominator because the bigger exponent was in the denominator. Okay, lots of details there. I hope that you're writing down your questions right now, so you will have chances to ask me live. Right now you're obviously just watching a video, so I know you're not able to ask right now, but please write things down, send me an email, and find ways to ask for help as needed. Okay, good. Are we done yet? Almost. There's one more little set of problems here we're going to see together. So we're almost there. and done with our first lesson. So take a break if you need to. We're almost there. Okay, so the last little section we're going to see here also deals with negative exponents. These are fractions raised to a negative exponent. So we're still following that process of flipping and making the exponent positive. Oh, and see, I even wrote it out. Here we go. So there, those are the things I was about to just rewrite for you. Flip the fraction. So see, we're not just flipping one thing. Because the entire fraction is in parentheses, we do still need to flip something, but it's the entire fraction. So a over b becomes b over a. And then the negative exponent changes to a positive exponent. After that, because there are parentheses, chances are we will need to use exponent rules like the power rule, probably, or others that we might need to use. Okay, so let's give this a try. 3 over 5 in parentheses to the power of -2. Okay, so let's try to follow this process here. 3 over 5, that's kind of like a over b. We're going to flip that to b over a. So let's flip it. 5 over 3. Why are we flipping it? Okay, I guess I should say when we have negative signs in math, you're probably just used to negative numbers meaning a certain thing on the number line, but so often a negative sign just means there's some kind of opposite happening or some kind of inverse happening. That's sort of what this is, okay? So the multiplicative inverse of 3 over 5 is 5 over 3. Multiplicative inverse is a fancy way of saying reciprocal or just you flipped it. Okay, so that's kind of why we're doing this. The negative sign is sort of a symbol that means we're going to take an opposite of some kind. In this case, it involves flipping a fraction. Let's keep going. Now that we've flipped it, we don't need the negative sign anymore. Now we just have a 2. It's positive. So step 1, flip the fraction. We did that. Step 2, change the negative exponent to positive. Yep, did that. And now do whatever we need to do to simplify. Okay, so we are going to use that power rule to simplify here and apply that 2 to both of these. So this is 5 squared over 3 squared. 5 squared is 25. 3 squared is 9. And we're done. So our final answer here is 25/9. I do not need to change it to a mixed number. We're not really dealing with mixed numbers really at all in this class from what I can remember. Everything can just stay improper. We cannot reduce 5 and 3 have no common factors. 25 and 9 have no common factors. So this is our final answer, 25/9. One more. Okay, so here's our second example. Let's do something similar where we're going to flip the fraction. So n to the 4th moves to the top. M squared moves to the bottom. That's the flipping part. And then my negative exponent, my -5, is now +5. Now we get to simplify again using the power rule. So we'll distribute that 5. 4 times 5 is 20. And then 2 times 5 is 10. So it's n to the 20th over m to the 10th. And there's no simplifying we can do there because n and m are not the same base. They're different variables, so we leave them separated in our final answer. So anything you're thinking of doing beyond this, nope, we're done. This is our final answer. Okay, so you should have a nice long list of lots of different exponent rules at this point. It's very detail oriented in this very first section. So there's a lot going on here. And I will just say, I don't necessarily think this lesson is the easiest one in our first unit. So if you're feeling a little worried, some of the ones coming after this, you might actually find maybe a little more understandable, possibly. Okay, good. So the last slide that I'd like to just point out here is this is sort of a summary of all the different rules that we just saw. Okay, so product rule, when you have a product, you add the exponents. Quotient rule, when you have a quotient division, you're subtracting the exponents. Okay, zero rule, sorry, zero exponent rule, anything to the 0 is 1. And some of the examples here are similar or identical to the ones in our notes. Some of them are slightly different. Okay, but there's some examples worked out over here. Power rule, when you see parentheses and an exponent on the outside of parentheses, that's when you multiply. Okay, so we saw this first example. We didn't see this one exactly, but you can work that out as well. Expanded power rule, that's where you're distributing the exponent basically to everything in the parentheses. Negative exponents were the last two, where you're flipping and then making the exponent positive. So that's our summary. We're going to continue using these rules in some of the sections that come after this. I'm going to end the video here, but I do want you to know I'm going to make a part 2 for this lesson just to show you some things in MyLabs Plus and just give you some extra information about homework and what's expected and what you're going to need to do in terms of showing work. Okay, so if you were in any of my classes in the previous quarter, in the spring quarter, things are a little different for the summer. So I'll save that for another video coming up. Okay, so we made it to the end of our first lesson. This was lesson 19. Good job making it through, and I'll see you soon. Let me know if you have any questions.